My paper is GPUs and Future of Parallel Computing, which is presented in I3 Micro at 2011.
And maybe what is the affiliation of the authors?
Affiliation is NVIDIA.
NVIDIA.
Yes.
Heckler, I think he's quite famous person in computer architecture. I think. I think he moved to NVIDIA.
Yes.
Okay.
Yes. This paper presented 3 challenges for parallel computing chips and their plans to overcome these problems. First is limited power budget, but this is already dealt in by processor, so I will skip. I just show one example. For example, supercomputer. The target power budget is 20 megawatts, and target compute capability is 1 exaflops per second. So to get this performance, we should achieve 20 picojoule per flop. However, modern CPUs 1,700 picojoule per flop, and GPUs 225 picojoule per flop. So we should achieve this 20 picojoule per flop. We should improve 85 times and 11 times more power per flop.
What is
Floating operation.
floating point operation?
Yes, floating point operation. To achieve this target, we should optimize instruction execution and data movement. First, instruction. Modern CPUs consumes their energy, too much energy to control logic. So, to get higher throughput, we should consume their energy to more useful work. It is computation. Today's energy consumption of double precision fused multiply add is around 50 picojoule. And data power dissipation is also large. For example, power to read 364-bit source operand and to write one destination operand consumes around operand to SRAM consumes around 56 picojoule. This is nearly same with DFMA operation. And read to the 3 operand and write 1 operand to 10 mm more distant SRAM consumes 6 times of DFMA operation, and this operation to external DRAM consumes 200 times more power.
So maybe the first 56 picojoule might come from register. The second 6 times scale may come from one chip cache, and the third 20x increase comes from off-chip DRAM.
Yes. So data movement power consumption is also very high. And with the scaling projection to 10 nanometer process, the ratio between the FMA operation, the arithmetic operation, and on-chip SRAM and off-chip DRAM memory operation is stay relatively constant, but the relative energy cost of a wire cannot be sustained constant. This means that energy consumption of data movement is growing as the picture size is reduced.
Because the wire, relatively wire length.
Yes, that
number.
Yes.
Okay. So wire delay is the issue.
Yes. So in future architecture, we should decrease the amount of memory movement by exploiting locality. This is very important. And second challenge is bandwidth gap between computation and memory. Memory bandwidth is growing slowly and computation bandwidth is growing much more faster. So the bandwidth gap between computation and memory is bigger and bigger. So how to narrow this gap is very important. Also, despite the memory bandwidth is narrow, but that power consumption is high. Because, for example, DRAM maximum bandwidth is 175 gigabytes per second, and this consumes 20 picojoule per bit. And total, this consumes 49 watts per second. This 49 watts per second accounts for 20% of total GPU TDP. So again, reducing data movement is very important. To cope with the bandwidth gap problem, architecture trying multi-chip modules. In other words, DRAM on chip and CPU plus GPU on chip. And 3D stacking, as the professor said, and deeper cache hierarchy to reduce this bandwidth gap. Also, we should utilize bandwidth very effectively by coalescing data and free-fetching data and compressing data. And the last challenge is parallel programmability. For parallel programmability, programmers should be able to represent their data access pattern and data placement. Because in GPUs, data model is not flat. Yes. And programmers also should be able to deal thousands of threads. And programmers should be able to choose what kind of processing course their task are running on. Because the architecture is changed to heterogeneous processors. Also, coherence and consistency should be relaxed to facilitate greater memory level parallelism, because the cost of coherence protocol is too high. The one solution the author said is give programmers selective coherence. This is experienced later. To cope with these three challenges, NVIDIA plans to make their architecture, echelon architecture, until 2017. The target is 16 teraflops per second double precision operation and 1.6 terabytes per second memory bandwidth, and power budget is less than 150 watts and 20 picojoule per flop. The whole diagram consists of 16 DRAM memory controllers and 64 tiles. Each tile consists of 4 throughput optimized core, it is GPUs, for parallel computing, and 8 latency optimized cores, it is CPUs for operating system or serial portion of a program.
So total how many cores? 256 plus 8? So 264?
Each tile has 4.
4 times 64.
Yes.
So 256 plus a CPU.
Yes.
So 264 cores. And total the target performance is
16
teraflops.
Yes.
Which is about 16 times bigger than Intel teraflop chip. So this is memory.
This is for graphics processing?
Yeah, graphics. Graphics usually have higher performance.
Yes. Also,
It's more parallel.
yes.
What is the power?
Yeah.
Power.
Power?
how much watt is power?
Power budget is their target is less than 150 watts.
That's the maximum budget.
Yes. And each tile consists of 4 throughput-optimized cores. And each throughput-optimized core has a secondary on-chip storage. In the paper, they said that these secondary on-chip storage may be DRAMs on chip.
Okay, so they start to integrate DRAM on chip because when I presented that slide, it's about 4 or 5 years ago, and it's starting to
Yes.
move to the industry. So here, what's the actual interconnect technology that connects this throughput optimized core? So this one is throughput optimized core,
Yes.
right? And what is this one? It's crossbar or what?
I don't know exactly what, but I think that this is a memory controller of on-chip DRAM.
This is crossbar connection. Any tire can connect with any crossbar connection. Crossbar.
Crossbar.
Crossbar connection.
Any point with any other point.
Um,
Like mesh connection, mesh.
I don't know. Mesh is different from crossbar. Crossbar is many to many.
Maybe
Mesh is just two-dimensional. That's different. And this is 256 kilobytes of memory. You have 4 bank. So this is 1 megabyte memory, right? This cache or what?
This is a sort of cache, but
This
yes.
is DRAM.
DRAM cache, yes.
One to DRAM. So each core has 1 megabyte DRAM. DRAMs are quite small, only 1 megabyte.
Yes, but they have off-chip DRAMs too.
This might be SRAM, and option might be here, right? I don't know.
Yes.
DRAM, it will be too slow for this processor.
Yes, next, in throughput optimized core, they had also SRAM in each lane. A throughput optimized core consists of 8 lanes, which can operate MIMD operation for divergent code and also SIMT operation for non-divergent.
What is SIMT? Single instruction multiple thread or what?
But yes, single instruction multiple thread.
Single instruction multiple thread. So this is more MMX, the data level current. Or
Yes, this is same as SIMD, but
SIMD.
yeah.
Okay, let's go back. Okay, so you say this is DRAM, not SRAM.
Yes, they told that.
So inside they have SRAM, but these are DRAM, and these are connected to other DRAMs. So this is only one tile, right?
Yes, one time.
One tile.
Yeah.
You have how many tiles? 4 tiles.
60.
64 tiles.
Yes.
So one tile,
Consists of 4 pieces.
and this interconnect connects core to the memory bank, and it also connects this core to the remote memory also, right? Through this interconnect, I guess, right? So two from this is NOC network on chip or something like that, right?
Yes, right.
And this bandwidth is 256 gigabytes per second and 64 gigabytes per second per TOC because you have one high and it's shared by 4, so it's total 256. And this interconnect is mass torus or what?
They didn't talk
mention.
that. Yes.
I think this is crossbar.
Crossbar.
No, it's not crossbar. Crossbar is not scalar. Okay, so I don't think it's crossbar. Okay. And this is the inside each core,
Yes.
okay? And you have L1 instruction cache,
Yes.
L1 directory. What is this L1 directory? Is it for cache coherence or what? What is the L1 directory?
I don't know exactly what because they didn't mention about
Okay.
that.
And this is L0
Yes.
instruction cache.
Yes.
This is L0 data cache. This is L1 instruction cache or data cache?
instruction cache, or they had elder instruction cache too for MIMD operation.
I see. Lane 0, and this is replicated in lane 8.
Yes.
And this is scratch.
Scratch
This is
pad is shared memory, SRAM.
SRAM.
Yeah.
And what is register file?
Yes, main register, they have two level register file. One is main register file, which is original, and one is operand register file. This is a sort of forwarding.
I see. Okay. So you can operate with MIMD, which is more like multiprocessors.
Yes.
So maybe they can assign iteration to every thread, every lane,
Yes.
and for all of them they can execute single instruction with different data, SIMD style.
Yes.
Okay, and two levels of register file, operand register file here,
Yes. And memory mainly.
main register file. So this is some second level register file. Back. So this is backed up by the second level register file.
Yes.
So okay, and register files is programmably can be moved from here to here, here to there.
Yes, they mentioned that.
And multi-level scheduling. So 4860 on that. What do you mean by multi-level scheduling?
In the paper, they built 64 threads at a time, and they differentiate 4 active threads and 60 on-deck threads. So when
So thread is running on each lane, or what do you mean by thread?
yes, in each lane.
But there are 8 lanes. Why only 4 active? You can have up to 8 active threads. Why 4?
I don't know exactly what.
They are saying that you can run thread on each lane.
Yes. So
Okay, let's go to the next one.
and they plan to give malleable memory system that which is selective SRAM. SRAM consists of hardware managed cache and scratchpad software managed cache. So programmers to determine the ratio of the hardware managed cache and software managed cache. For example, 16 kilobyte software hardware managed cache and 48 kilobyte for software managed cache. So programmers can determine the cache each to inherited by where the portion of memory. For example, cache can inherited from global memory (DRAM) or cache inherited from L2 cache, and programmers also choose the range of the DRAM.
So maybe in the address space, some of them are, some area might be hardware controller, some area
Yes.
might be software. Software controller, what kind, how do they control by software? By the compiler or
By the programmer.
by the program, by the compiler?
Yes.
I see. So program explicitly say,
Yes.
we want to move this data into this cache.
Yes.
And then
And to make writing a parallel program as easy as writing a sequential program, they plans to give unified memory addressing because GPU memory system is not flat. This is important to code easily. But when I examined, already AMD shows their unified memory addressing technology, which is called HUMA. And selective memory coherence. This means that a programmer can choose the cache memory is coherent or not. So first, we can code the program in coherent protocol and then the program is stabilized. We can remove the coherent protocol for efficiency. And hardware fine-grained thread creation. This means that first programmers just give hardware coarse-grained thread, then hardware is automatically find fine-grained parallelism. That is the end.
Okay, very good paper and very good talk. So I'll give you 5 bonus points. Okay? Okay, so last chance for 5 bonus points for today's presentation. Okay. So for all of you who present today, send your slide to Changyeon, YUNCH, and Changyeon. So post on the web, okay? And with the date. Present. So all the other students, you must present next week, okay? Because you need to present at least one. 2 paper presentations will get prepared. 미디어 발표는 아니 이거 말고 페이지. 지금 마이크로프로세서의 재밌게 했었으면 이스카에 나왔던 것 중에 좋은 거를 전화기 같은 것도 하는 거고 커머셜 프로덕트에서 드시면 논문 자체가 좀 많이 나아요. 하기 편하게 좀 더 리파인드 있습니다. 안 되나? 웹에서 다운받을 수 없어? 이메일로? 자기는 내가 NVIDIA에서 장난이야. 인텔 어려워? 논문도 찾아봤어? 뭐 어려워?
교수님, 제가 그 이메일에 따로 보내는 건 없고 제 컴퓨터랑 원격 연결해가지고
할 수 있으면 해도 돼. 오늘 또 발표할 사람 있나? 뭐 다른 사람 다 next week?
발표 시작하겠습니다. Hi, I'm Junami. Today I will introduce low power real-time object recognition process for mobile vision systems.
Low power real-time object recognition processor for mobile vision system. Okay. And this is from KAIST, I guess, right? Okay.
This is all outline of my presentation. So that picture I think that picture was captured by me. First thing is introduction. Let's see this. Yes.
It's okay.
내 몸을 바꾸는 슈퍼 발효 푸디스케어.
내용 발음 시켜줘.
다음 소식입니다. 스스로 가고 스스로 멈추는 자동차와 혼자 알아서 주차하는 자동차. 공상과학 영화에서만 볼 수 있었던 모습이 아닐까 싶은데요. 자동차와 첨단 기술이 결합을 하면서 운전자들의 편리성이 높아지고 있습니다. 김재희 기자가 취재했습니다.
자동차 계기판에 물체가 나타납니다. 이 물체가 가까이 오면 사람인지 동물인지를 인식해 운전자에게 알려줍니다. 자동차 앞쪽에 달린 적외선 카메라가 300m 밖의 물체를 인식해 운전자가 미리 대처할 수 있도록 알려주는 나이트 비전 기능입니다.
야간에서 운전을 할 때 일반적으로 가시거리가 짧기 때문에 운전자의 사고에 대해서 상당히 많이 위험에 노출이 될 수 있는데요. 그런 적극적인 안전에 중점을 둔다고 볼 수 있겠습니다.
일렬 주차에만 적용되는 주차 보조 시스템은 다양한 상황으로까지 진화했습니다. 뿐만 아니라 좁은 공간에서 차량이 빠져나오는 기능도 선보였습니다.
주차에 어려움이 많으신 여성분들이나 아니면 초보 운전자분들을 위해서 주차를 하시는데 좀 더 편리하게 도움을 드릴 수 있는 거지 너무 맹신하시면 또 안 돼요.
브레이크나 가속 페달을 밟지 않고도 스스로 가다서다를 반복하는 자동차. 갑자기 튀어나오는 물체를 인식해 수도를 방지하는 시스템까지.
자동차가 첨단 기술.
How was this then used? Nowadays, electrical automation system is in the limelight, especially object recognition is the most in limelight. So how we can implement object recognition system? So we require real-time operation, and also if we can, the system have to need high performance and low power operation in mobile system. Also, when we implement this object recognition, we have to find a suitable algorithm like SIFT algorithm and hardware optimization, and parallel computation. Next thing is background. I'll say I will introduce background knowledge. Do you know SPT algorithm? That is scale invariant feature transform. This is the most popular candidate for how to extract some interest points out of the object and describe them. Also, that this algorithm robust against change in transform, scaling, and rotation. What is the problem in SPT-based object recognition? It consumes a lot of power, owing to having computation requiring descriptor generation and matching. And today's high resolution image sensor and tight power budget, it makes real-time SPT implementation in mobile device even harder. Next thing is main idea. So how can we solve the problem? The first, make an object recognition processor using an attention-based recognition algorithm. They propose. It is used for energy efficiency. I will say that next slide. Also, make use heterogeneous multi-core architecture, and for this multi-core architecture, they use NOC communication. In attention-based recognition algorithm, they use Roy part of image. They use Roy part of image. That mean Roy mean region of interest. That can minimizing unnecessary computations. Also, they use heterogeneous multi-core architecture because it provides several types of parallelism and achieve high throughput and low power. It can low power consumption. Also, they use NOC because high bandwidth of NOC play role as the communication backbone.
Okay, so this is the architecture of their design.
No, there is
just concept.
Yes.
Okay, so you have network on chip. So you have MPEG. This is actually the hardware aging, right? And you have CPU and you have graphics. So these two are processors. Okay, and each one is connected to this. What is this? Can you read it?
Request network.
Request network. You go. So this is reply network or something like that. This one's network.
Yeah.
So this is network on chip.
Yeah.
And it's going to media interface, SRAM, and DRAM controller. Okay. So.
Okay. So why use why find ROI? Many image processing algorithm has no regard throughput. For example, edge detection. That image has 480 by 316 size. If you compute that image serial, you have to compute 172,800 times for finding object feature. But the object has its own feature in image, so you can select part for reduced computation. there is table over there's processor. They propose image processor for object recognition. That name is ONV, based on chip network vision. ONV1 and 2 limited to simple detection or instance tracking because it is implemented by conventional shift algorithm. So it just used for small module that do require accuracy. For this reason, they have evolved to process higher resolution video stream with better fidelity, throughput, and energy efficiency for more complex and noisy environments such as Bond 3 and 4 and 5. Main idea have applied in this model.
So, okay, let me go back. So this bone file is the
They focused on
design we discussed
Yeah.
in this paper.
Yeah.
So it has multiple object perception and context-aware vision, attention, and so on. And SMT enabled multicore, so they use some kind of multi-threading also.
yeah.
And it's a small power compared to processor. And they use 0.13 micron process technology. This is the chip size. Okay.
There is algorithm part. The algorithm name is attention-based object recognition. The algorithm mainly consists of two stages: object attention and tile-based object recognition. As figure 1, object attention consists of three parts. First thing is applied in V3. They generate silency map that can extract object feature using color, intensity, and orientation. But it is very slow. Because of pixel level parallel computation. So it doesn't consider Roy area. For increased throughput, they divide the image for parallel tasking. This technology applied to Bond 4. Future object is integrated in database after splitting matching. And last, our technology applied to Bond 5, like 3 and 4, applied to mobile vision processor that has high resolution. It has to robust to noise. To migrate this problem on V5, exploit the temporal familiarity map, which measures the temporal coherence of consecutive frames by tracking the recognized object in previous image. And the tile-based object recognition includes feature extraction, key point description, and key point matching. This is progress of object recognition. Their idea is object attention part, and tile-based object recognition, just shift-based.
Okay, so let's go back. This one is the algorithm they run on their processor. Okay, so this is implemented in software, right?
No, hardware.
Hardware.
Yes,
So-
they implement chip.
So hardware, you mean it's running instruction or it's just aging? Aging? Okay, so they have this chip. So let's go to the next one, next slide. Where is the chip? Where is the hardware? Image processing engine. Where is it?
I will say this slide. That they use this architecture to realize tile-based recognition with increased DLP and TLP.
Right. Do you know my question? My question is this processor or hardware?
It is processor.
That means it's learning program,
Uh,
right? Processor means you run instruction. Okay?
yeah.
So that's why it's called instruction level parallelism or data level
Yeah.
parallelism or thread level parallelism. All this means they are running applications. But this processor is optimized for this computer vision application.
Yeah.
And they run this application in the previous slide. Right? So this one is the newest one.
Yeah.
Okay, so you have network on chip. Okay, and you have SIMD, dual SIMD modules and MIMD modules. I'm not sure about MP. This is what MP multi-core or multiprocessor or
Matching processor.
matching processor.
Yeah.
This is matching processor. This is another MIMD core. This is SIMD core.
Single instruction multi-data.
Okay, and each core is running different application. This GF means GF, Gaussian filtering.
Yeah.
And so dual, is it dual what? So you have separate core for each one or GF, DOG means
Separated.
separate. So each one is a separate core.
Yeah.
So some of these hybrid. This is dual core, this is SIMD core, this is what? 013.
There is a GF and DOG and LST consist of each dual SIMD. That
Okay, so this is just single core, dual core, SIMD core, right? So you have 4 SIMD cores, dual cores, or what? How many cores here? How many processors?
four SIMD core and 16 multiple instruction multiple core.
SIMD cores.
Yeah.
And this is what do you mean by dual? Is it dual core? Each core is dual or dual thread? Or what?
Dual thread.
Dual thread. So this is one SIMD 2A multi-threaded core. We have 4 cores, SIMD cores, and this is MIMD core. This is not multi-threaded.
The what?
It's a single thread.
It just can single thread.
Single thread. So we have 16 cores. So this is normal multi-core. Normal multi-core. This is SIMD core, 2A multi-threaded, and this is what? This is processor or hardware?
So, SIMD cores used for GF and DOG, LOC.
How about MP? MP stands for what?
MP, main core used for MP.
Main core? Main core what? MP stands for what?
Main core used for MP.
What is the MP?
Matching processor.
Matching processor. What is matching processor?
In tile-based object recognition, key point matching is necessary.
It's doing matching. So what kind of processor? Is just general purpose processor or what?
Not general purpose, just to
Do the matching.
Yeah.
So is it hardware or processor? Do you know the difference?
I exactly, but I think it is.
No, there is a distinct difference. Processor means it's running software application. It's running instruction. Hardware, I mean by hardware means it's just MPEG. It's just hardware. Given input, it just produce output. There is no instruction running. Is it hardware or processor? MP, magic processor. You don't know.
I don't know, but they said in paper that just to matching key point, just to use for key point matching.
I know. I'm asking whether it's hardware or not. You don't. So your answer is you don't know. Okay. Okay, let's go to the next one. Now.
To realize tile-based recognition with increased DLP and TLP, they proposed six task level recognition pipeline for higher throughput and system utilization.
So this means 5-stage fine-grained pipeline. So this is pipeline.
Yeah.
So the first perform GF, which is Gaussian filtering, and then DOG. Right?
Yeah.
DOG is difference of Gaussian, and LOC, localization, and KD, key point discretion, and finally FM, feature matching in parallel. So they send some pixels in this pipeline and it's over this pipeline stage. It's not actual instruction pipeline. It's actually, you can think of this as execution pipeline, right? Back-end pipeline. Feature processing is done by this stage, right? And this is number of threads are 8 because you have 8 here and 8 threads. Performance core 47,700 what is per second? What is this? Tile? Tile.
Low tile.
Okay. Region of interest tile. Okay. And vectors per second. Okay. So compared to this one, they improve our performance by 3.5 times compared to this version 1, version 3.
Yeah.
Okay.
To accelerate each sector algorithm operation, they propose using several multi-core processors with optimized data parallelism and pipeline architecture. On V3, heterogeneous SIMD architecture uses 16 very long instruction word-based SIMD processing element for future extraction stage. With the subsequential feature matching stage executed in the matching processor, it comprised a two-stage task level pipeline of shift-based recognition. This architecture only provided low SIMD throughput.
Okay, so this looks like they go into this pipeline in this order. So they, through the network, they maybe receive packets or pixels, and they go to this. Here, they first do here GF, DO, JLOC, they send to KD and FM complete. Okay, next slide.
Next.
Yeah, next. Okay.
The main processing cores includes the throughput optimized pack, the latency optimized FMP, and the power optimized machine language engine (MLE) for different shift operations. The spec performs the feature detection and key description operation to generate the shift descriptor.
Okay, next one.
Next slide is implementation. Let's see the figure 5. Let's see the figure 6. Figure 6 shows the floor plan of the V5 prototype chip, and table 2 shows the chip summary. It is fabricated with 0.16 nanometer CMOS process, micrometer. In figure 5, this graph shows the performance comparison of BOM V series. As the result, both algorithm and architecture optimization are important. Also, in result of this type of BOM V5, instruction and task scheduling is the most important for high performance. And table 3 compares the BOM V5 with the GPU. It means general purpose computing on GPUs and mobile vision processor for feature extraction or object tracking recognition. In object recognition algorithm, BOM V has good performance beside low level process and low frequency. And last thing is conclusion. Energy efficient system is important to improve performance, and algorithm and architecture have to optimize at the same time. BOM V multi-core processor can apply real-time object recognition system, and future BOM V processor will further lower the power consumption.
Okay.
And last thing is evaluation.
Okay.
I think table 3 has to contain the result that comparison of other recognition processor, because they just compare with GPU. I think it is not reasonable.
Which one? NVIDIA?
All of them are GPU, but it just used for object recognition.
Right. So they compare to this. This is GPU. This is cell processor. This is not GPU. This is Sony PlayStation 3 engine. Okay. And this OMAP is just mobile multimedia processor, and this is for automobile industry. And this is some academic processor from Michigan. And so they compare to each processor or what?
I think this comparing results not reasonable, because their processor BOM V just used for object recognition, but other processor used for most general purpose.
Those are not general purpose. The target is different. It's okay. They can compare, but they are much. The chip size is much bigger, high speed, and much expensive. This is much small chip. With this 0.13 micron process technology is also old technology, so it's okay. So let's look at the evaluation slide. So
Also, when hardware optimization, not only overall algorithm, but particular algorithm block optimization are needed. I implemented object recognition used applied codic-based gradient and
you or the authors? You. Oh, you. Okay, so
I was
who is your advisor?
정선.
박종. Yeah. So you are working on this field, object recognition, or what?
No,
Which area are you working on?
digital circuit.
Digital circuit. Actually.
I was compared codic-based gradient, codic-based computation for gradient and magnitude. They just use compare between codic-based and conventional shift algorithm. I think codic-based object recognition more efficiency in power.
So you think this codic-based algorithm should be more efficient than their algorithm in object recognition. And so this evaluation is your evaluation. Your evaluation. Table 3 is not fair because they are comparing their target application optimized processor to other general purpose. And okay, that's one. And the other is you think these are more efficient algorithms compared to their algorithm they implemented in that. That's your evaluation. Okay, actually. Is it? Okay. Good talk. Good job. Okay. 오늘 수고 여기까지 합시다. 수고했어요.